Okay, so like I was saying, today will be your last lesson for your stat class is chapter 26, which will be inference on the linear regression slope. So I think this PowerPoint has like a lot of details that you can come back and look at. I'm just gonna go skip to actually doing the example. This is just some details you can come back and read. Okay, here we go. So on your notes, it explains to you the 5 steps on doing a hypothesis test for the slope. So here are the steps that you'll need. Step 1 is to define your parameter. So now our parameter is no longer a proportion, no longer a mean. Your parameter now is the slope of a linear relationship, and we're going to use the Greek letter B, so it's called beta, for your parameter. So you would define it as like beta equals the true slope of the relationship between or height and weight, or between test grade and hours studying, whatever your two variables, your two quantitative variables are. So that would be step 1. Okay, the hypothesis, you need to know these. For a linear regression test, your null hypothesis will always be that there is no linear relationship between your two variables. So assume there is no relationship between height and weight. The alternative will be that there is some type of relationship, and that just depends on the question. If the question wants to know, is there a positive relationship, then you can put positive linear relationship, or maybe a negative relationship. If it doesn't specify positive or negative, you can just go with there is some type of relationship. And that's how you would write your alternative hypothesis, your HA. You could also write it with symbols. So instead of writing it with words, for example, the null hypothesis, like I just said, is we assume there is no relationship between X and Y. So therefore, you could write beta equals to 0. Like you can write that the slope of the relationship between X and Y is 0. So that still just means there is no relationship, no linear relationship between X and Y. The alternative, like I said, it depends on the question, but if you're just looking to see if there's any type of linear relationship, you could just put beta doesn't equal to 0. And if that's the case, that means that there is some type of relationship. Sometimes they'll ask you, like, is there evidence for a positive linear relationship? And in that case, you would put beta is greater than 0. Or if it wants a negative linear relationship, you would put beta is less than 0 for your alternative hypothesis. So that would be step 2, write some hypotheses. Next is the conditions. So the conditions for this test are like the longest one ever. So here they are. I guess I'll just read you the names and then we'll actually do them in the example. But you're still going to be checking your randomization condition. Okay, now you're going to be checking something called the linear enough condition, the equal variance condition, and then your normal population condition. We'll explain them specifically once we start the example. That was step 3, check the conditions. Okay, step 4 is going to be to get your p-value and your test statistic. You will have to memorize this formula, I guess, for the test or for the AP exam. The test statistic is going to equal to regular B, which is, this is the slope of your sample. So B is the slope of your sample data, minus beta, which is what we assume is the population slope, divided by the standard error of the slope. So this SEB stands for standard error of the slope. So on your quiz, you can use your notes because it's asynchronously, but on the test, you have to have this memorized. And obviously for the AP exam, if you're going to take it, you're going to have this memorized. So that's step 4. Use your test statistic and find a p-value. Linear regression slopes require a t-distribution. So it is a t-statistic, t-distribution. So we'll do like a t-CDF for finding the slope. And then final step. The final step on any hypothesis test is to make a decision and conclusion based on your p-value. So depending on how small your p-value is. This is kind of what I was just talking about. You can read through this by yourself. I think this one's important. So linear regression is a t-distribution, like I just mentioned, but the degrees of freedom for this distribution is going to be the sample size minus 2. So that's another thing you have to remember. When we did sample means, that degrees of freedom was n minus 1. But now when you're doing linear regression, your degrees of freedom will be n minus 2. So you have to remember that. So here's the formula for a confidence interval. We'll come back to when we do that one in the example. Okay. So I think we'll come back and visit this one as well. So these are all the formulas that you'll need. There's something, like I just told you, your test statistic is B minus beta over the standard error of the slope. You will have to know the formula for the standard error of the slope right here. So I've given it to you here. You don't, yeah, pretty much you have to memorize it because you're going to have questions that are asked you about the standard error of the slope. So that's another one you get to memorize. So here are the formulas that you'll have to memorize for your test and for the AP exam, and then understand them. We're going to just come back to them when we do the example. Okay, so there we go. So now we're ready for some math. So like I said, get your calculator. Example number 1. It says, car dealers across North America use the Blue Book to help them determine the value of used cars when their customers trade in when purchasing a new car. The book lists on a monthly basis, the amount paid at recent used car auctions and indicates the values according to the condition and optional features, but does not inform the dealers as to how the odometer reading affects the trading value. So in a study to determine whether the odometer reading, so how many miles a car has, should be included, 10 5-year-old cars of the same make, model, condition, and options are randomly selected. So we do have a random sample. The trade-in value and the mileage are shown below. So on your notes, you see your table. So basically it's asking you, is there evidence of a negative linear relationship between the number of miles that the car has, which is the odometer reading, and the trade-in value? And probably yes, because the more miles the car has, the less it'll be worth. But we're going to do the whole test to prove it. And step 1. So I guess here goes the steps. Step 1. We need to define the parameter. The parameter for your slope test will be a beta. And you would say beta equals the true slope of the relationship between, I went ahead and just used X and Y, but then you have to define X and Y. So X would be the odometer reading, so how many miles the car has. And Y would be the trade-in value, since the trade-in value depends on how many miles the car has. So step 1, I have defined my parameter. Beta equals true slope of the relationship between odometer reading and trade-in value. If you want to use just X and Y, make sure you define X and Y, like I just said. Step 2, write some hypotheses. So why don't you head and try by yourself? Remember I told you the null hypothesis is that there is no useful linear relationship, and you can write it with words or with an equation. The alternative hypothesis should be, is there evidence of a negative linear relationship between X and Y? So all of this information you'll see on your AP Classroom quiz as like multiple choice. So make sure you choose the right ones. But here's what I wrote for my hypothesis. It looks like I just did them in terms of an equation. So for the null hypothesis, I put assume that the slope is equal to 0, so no linear relationship. For the alternative, I put we want to know if there's a negative linear relationship, so slope is less than 0. And that was step 2. If you have any questions at any point, please just let me know. Now, I guess now we do the conditions. So the conditions are the ones, like I said, they take forever because this is the longest conditions out of all of the tests. So conditions. Number 1, randomization condition. That's always the same as all the tests. Assume we have a random sample. Oh, I forgot to put a little animation on this box plot here. That's okay. Animation. Add. Earlier. I'm just trying to fix my box plot. Okay, you keep reading through the rest of the conditions. I think I fixed it. Okay, let's see. So, okay, randomization condition. The problem says we have a random sample of cars. So write it down, I guess, or just save it. Okay, so if you look at the top of your notes, the next condition is that it's called a linear enough condition. So in order to actually do the calculations in the test, your data should be linear enough. So the way we would check to see if your data is linear enough is it says assume that the true relationship is linear. So the way you would check that is we want to sketch this data into your calculator and look at a what's it called? The scatter plot. Make sure like the little dots look linear enough and not completely, just make sure they look linear enough. And then also, if you go back to like linear regression from last semester, for the data to be linear, appropriately linear, your residual plot needs to be random. So let me remind you how to do all this stuff on your calculator. So I'm going to show you how to do a scatter plot one more time, and then I'm going to show you how to do a residual plot one more time. So wake up the calculator. For starters, you're going to need to type in your data in a spreadsheet. So I guess let's type it. X was the odometer reading, which is the miles in thousands. Let's just put 59. Let's just keep it like that. And then Y was the, oh, don't forget to label it X and Y. Y was the trade-in value in hundreds. 100. So hopefully we typed in everything correctly. So what we want to do right now is we want to go look at the scatter plot of this data and see if it looks linear enough. So the way you do a scatter plot is once you've typed in your data on here, you do doc 47, I think. Doc, insert, yeah, data and statistics. So document 4, insert 7, data and statistics. And you click on the x-axis to add your x variable. Make sure you've labeled your data as x. And click on the y-axis to add your y variable. And I have no idea. Try and see if it works. So this is your scatter plot. And technically, you're supposed to put a sketch on it on your paper, I guess, if this was for response. You don't have to label you have to label the axes, but you don't have to like scale it. So I just did like a sketch of this scatter plot on my paper. Your whole quiz on the AP Classroom is multiple choice. So I guess you would just, yes, the conditions are met, or no, they're not, or yes, it looks linear enough. So where's my little, okay, so the animations don't go in the right order. But anyway, so here's my little sketch. I sketched the scatter plot, put X in the x-axis, Y on the y-axis. I sketched the little scatter plot. And it looks linear enough, so I just put the scatter plot looks linear enough, so we're going to go with it. So that's linear enough. It does look like a negative relationship. But now you have to do the residual plot. But in order for you to do a residual plot, you first have to run the test. Like you have to do the linear regression first. If you don't do a linear regression, then you can't see a residual plot. So what we're going to do is we're going to actually run the test or do a linear regression to see the residual plot. So to do that, you're going to have to go back to the spreadsheet and actually do the linear regression test. So back to the spreadsheet. So on the spreadsheet, let's go ahead and just find the linear regression test so that we can see the residuals. So one way to find it is under menu, stat, test. You can just go find the one that says linear regression t-test. On my calculator is letter A. It's linear regression t-test. So if you do this, it's going to give us everything that we need, and it's going to show us a residual plot. X list, I called it X. Y list, I called it Y. Save the regression equation. You can just save it as F1, that's fine. Frequency list, you can just leave that as 1, that's fine. Alternative hypothesis, we said less than 0, so change that. Less than 0. First result column, you can just leave it as whatever it is. You're just going to save it in that column. Press OK. Okay, so this gives us a lot of information that we'll come back and use. For example, it's going to give you your test statistic, like your t-score. It's going to give you your p-value. It's going to give you your degrees of freedom, which is 8, since you do sample size minus 2, and 10 minus 2 is 8. It's going to give you like the slope of the data, the y-intercept of the data. Oh, it's also going to give you this SE slope. I guess we'll come back to it. For now, let's just go do the residual plot. So now that you run the test, now you can take a look at the residuals. So to do the residuals, I would just add another graph. So let's do that doc47 again. Doc47. And in a residual plot, the x-axis, it's still x. So for the x-axis, still go ahead and click X. And then on the y-axis, now you put residuals. You see, now you can see the residuals because you've done it. I think the stat.resid, that's always like the most recent one. So I would always go with that one. And this is called a residual plot. I'll try to find, I have a document that tells you how to do the scatter plot, residual plot from like last semester. I'll try to find that and add it again to Schoology. So this residual plot tells us that since it does look random enough, like there's no curved pattern or there's no clear pattern, that means that your data is linear enough to do the test. So on my condition for the linear enough, I would say the scatter plot looked linear enough with like a negative relationship, and the residual plot looked random enough. So that condition is good and met. And like I said, if it's free response, you're supposed to show a little sketch of your scatter plot, and you're supposed to show a little sketch of your residual plot. Your residual plot has X on the X-axis, and it has residuals on the Y-axis. Sometimes you can just use E for like error, so those are your residuals. So after all of that, now you have the second condition checked, the linear enough condition. The next one, the next condition is called equal variance condition. I'll read it to you and then I'll try to show you what it means. But in the equal variance condition, it says the standard deviation about the line is the same everywhere. So basically what you need to do is you need to draw the line of best fit on your scatter plot. and you need to look at the scatter of the data points about the line, and they should be roughly the same. Basically, like, you don't want to have like any outliers with like really large residuals. So here's a sketch of my scatter plot. If you were to just to draw a line of best fit, like the line that fits through most of them, we notice like we don't have anything that's like a complete huge outlier in any direction. So like this would be good enough. So here you would say the data appears to be equally scattered along your line of best fit, or it's called the least square regression line. I think I spelled that backwards. This should be the least square regression line. So if it was for response on your scatter plot, you would just draw a line of best fit, and then you would just look to see that there's no like outliers. So for now, that looks good enough. The data appears to be equally scattered along the line. Like I don't see anything with high residuals. That's called equal variance condition. You could also draw the line of best fit on your scatter plot on the calculator if you wanted. Finally, the last condition for this is number 4. It's called the normal population condition. So in order to check that, it says that your residuals, so we need to look at the residuals again, not the residual plot, but like just the residuals alone. Your residuals need to be like normally distributed. So in order to do that, we need to take a look at the residuals and maybe draw a box plot or a histogram of the residuals only. So let me show you how to do that on the calculator. So again, this one, you don't want the residual plot. You just want just the residuals, one variable only. The way you would do that is back on your calculator. That's just the residual plot. I don't need that. Okay, what I would do is back on the spreadsheet, I would add another graph. So let's add another graph. So doc for 7. And now we only want the residuals. So that means that on the x-axis, you only put residuals. So one more time, add another graph, and this time on the x-axis, go ahead and only put residuals. And now, okay, right now you can't see the distribution of these residuals, so you need to change the plot type to a either box plot or histogram. I like box plots. So let's change the plot type. Menu, plot type, and I guess box plot is good. And here's where you're looking for. You're looking to see that the box plot looks fairly symmetrical with no outliers. This one looks a little bit skewed to the right, but overall, we're just going to pretend it's symmetric enough to continue. Yeah, because like from the median to the min, looks about the same as from the median to the max. In terms of like the Q1 and the Q3, it does look a little skewed to the right, but we're just going to go overall fairly symmetric enough with no outliers. And that's to check the 4th condition. So where did my PowerPoint go? So for the 4th condition, it says the normal population condition. The box plot of the residuals looks fairly symmetrical with no outliers. So I'm just going to go with it and sketch a picture. Obviously, this would be easier if it was for response because you can show your work and you can explain, I feel like this is symmetrical. And that's how you check the conditions for a linear regression test or a linear regression interval. Since these are like super long, I have seen questions on the AP exam where like all you're doing is just checking the conditions, and then that would be like the end of the problem. They wouldn't ask you to do more. So I think on your quiz in the AP classroom, you will be asked multiple choice questions about the conditions. So make sure you use this. These are the conditions, and here's how you check them. So now, assuming that everything looks good with these conditions, we can move on to finish this test. The next step is to actually do your calculations, and that involves just using the calculator. But There is a formula for the test statistic, which is a t-score, and that equals to the b minus beta, which is b is the slope of this data. We can find it using the calculator. Minus beta. We assume that beta is equal to 0, so that would be 0. Divided by the standard error of the slope. That's again given in the calculator. So let me show you where to find these numbers. It's on the spreadsheet that we did the test on. So if you go back to the calculator, go back to the spreadsheet. Remember that when we did the test, and in case you forgot how to do the test, remember we just did menu, stat test, linear regression t-test. Okay. So here's everything that you'll need. Like I just told you, I already know the test statistic, negative 5.6. I already know the p-value, almost 0.0002. But if I do want to find like all the little individual information, just keep scrolling down to find what we need. So here's A and B. When you do the linear regression, the way I did it here, A is the y-intercept of your equation, like y equals A plus bx, and B is the slope of the equation. So this is the slope of this data, and that's what you're using on your test statistic formula. So notice that B was negative 0.2668. So that's where I got this, negative 0.2668. Minus 0, because that's what the null hypothesis assumes. And now you have to go find the standard error of the slope. So keep scrolling down on your calculator. We'll come back to that one. There it is. The one that says SE slope, that's the standard error of your slope. So that's the denominator, 0.047.
What if that one doesn't show up on your calculator?
Oh, yeah. I think if you have an 84, I remember this, I guess like from years ago when I used those, it doesn't show you the standard error. So what I used to do back when I had that is this, Joseph, like I know it shows you the slope, like this one, right?
Yeah.
The slope. And then it also does show you the test statistic, right? So I would work backwards to find this. Like that's just unknown. So I guess cross multiply divide, and you would work backwards to find it. So you might need to do that if you're going to use that calculator, or I suggest you use one of mine. But it's not that bad. You can find it. So for the rest of us that have an Inspire, we can just copy this 0.047, standard error of the slope. So now we know that that's, if you were to do the calculation, or if you just copy the calculator, your test statistic is negative 5.625. Now we can find a p-value. And again, the calculator already told us the p-value. It was like 0.000 something. But the way you would find the p-value, I guess, manually sort of, is since your alternative hypothesis was the slope is less than 0, I would want to find the area where t is less than negative 5.625, and that involves a TCDF. So if you're required to show your work, you would show TCDF of negative infinity to negative 5.625. So your lower bound, upper bound. And then, like I told you, the degrees of freedom should be 8 because it's n minus 2 for the linear regression. So if you were to do that on your calculator, we don't have time to check, but if you were to do that, you will get the 0.0002. So there it is, 0.000248. And finally, to finish the test, make your decision and your conclusion. Since that p-value is really small, you would say, I reject the null hypothesis, and there is evidence of a negative linear relationship. Since the p-value is less than 5%, I reject the null hypothesis. There is evidence of exactly what I just said. There is evidence of a negative linear relationship between the odometer reading and trade-in value. I'll pause for questions, and then we'll do the confidence interval. Okay, so now that we've done a test, we can continue using the calculator to show you how to do the confidence interval. So letter B says to construct and interpret a 90% confidence interval. So basically the steps for the confidence interval are similar as a test. You're supposed to define your parameter, which we already did, like beta equals. You're supposed to check some conditions, which we already did. And now you're supposed to use the formula for the interval and use your substitutions. So this is the formula for an interval for the slope. You start with B, which is the slope of the specific data, or the slope of your sample, plus or minus T star, which is your critical value, and then times the standard error of the slope. So again, everything's in your calculator. Like we already found B. If you remember, or if you go back to the calculator, we know what B is. B was the negative 0.2668, which was the slope of your sample, plus or minus the way you would find your T star is with an inverse T. And remember, since you want the middle 90%, you'll have to put 0.95 here for the area, and then comma degrees of freedom. And the standard error of the slope, again, you can find it on your calculator if you scroll down. Or if you have the older version of the 84, you just have to work backwards and get it. Now you can type that manually into the calculator to get the interval, lower bound and upper bound, or let's just do the interval on the calculator to get the answer as well. So on your calculators, still on the spreadsheet, let me just scroll over. This time, let's go find what's called the linear regression T interval. Menu, statistics, this time do intervals. It's the one that says linear regression T interval. Interval for the slope. Yes, we're doing the interval for the slope. Remember, we call the X and Y. Store, you can just leave that blank. Frequency, leave it as 1. Confidence level, this is 0.9. And then you can save your results wherever you want them. So if you do that, what is toxic? Okay. So this is my interval. That was just the equation A plus BX. So it automatically gives you the lower bound and the upper bound of your interval. So you could copy that, negative 0.355 and negative 0.178. I think on your AP Classroom quiz, you will be finding an interval, and you can just use the calculator to get your answer. You don't have to show work on the quiz. The slope is the negative 0.2668, which we already knew. ME is the margin of error. If it asked for a margin of error, that's what it would be. Degrees of freedom. And then standard error of the slope. That's my answer, negative 0.37 to negative 0.15. Was that right? Negative 0.35 to negative 0.17. Wait, why is it different? Which one's right? The negative 0.355 or the negative 0.37?
I got the negative 3.55.
Aiden, what about you?
0.35.
Oh, okay, so then this key is wrong. I don't know where I got that from. Let's fix it. Thank you. And now you're supposed to interpret it like we are blank % confident kind of thing. So see if you can interpret that while I fix my answer key. So it should be negative 0.355 to negative 0.786. So does it look right now? Okay. Oh, and then I have to it's between. So you would interpret your, oops, it's okay. The video is still okay. You would just say we are 90% confident that the true slope of the relationship is somewhere between negative 0.355 and negative 0.17. Obviously, it is negative, so we do have evidence that the slope is negative, and which is going to help you answer the last question, letter C. Based on your interval, would you still reach the same decision and conclusion? Like, would you still remember your decision was I rejected HO? We do have evidence that the slope is negative. So this should always be a yes answer if you did everything right. So based on my interval, I do have evidence that the slope is negative because the whole interval is negative. But basically you would say, since the null hypothesis of the slope being zero, like b equals zero, is not in this interval, you can reject the null hypothesis and conclude that the slope is negative because the whole interval is negative. So I'll give you time to write that down. Save it. And let me pause for questions. So like I was saying, last thing you got to know for your stat course is you do need to know, I guess just memorize the formula for the standard error of the slope, because there's always questions on the AP exam that ask you to describe like the effects of the standard error of the slope based on this formula. So let me try to explain to you what the formula stands for. For starters, make sure you memorize it. But the standard error for the slope is equal to S over the square root of n minus 1 times S sub x. So here's what each of these represent. And it's on your notes if you have the printout. So tiny little s on the numerator stands for the standard deviation of the errors around the line. In other words, like the standard deviation of the residuals. So that's what this S stands for, the standard deviation of the residuals, or the spread around the line. N stands for your sample size. I didn't put it on there because I guess it was just given, but N is the sample size, minus 1. And now the S sub x, that stands for the standard deviation of your x variable. So the spread of x, aka standard deviation of your x variable. So now here's a type of questions that I've always seen on the AP exam, at least one of these. So if you look at examples 2 and example 3 on your notes, let's go ahead and try to answer that based on this formula. So example 2, if you want a regression equation with the smallest standard error of the slope, so you want this SEB to be the smallest possible, which of these lists would you use for the values of the explanatory variable? So basically these are the x variable. So which of these x variable lists would you use? Assuming that each conditional distribution of y has the same variability. So if this part here, this last part, assuming that each conditional distribution of y has the same variability, that's just telling you, like, assume that the numerator is constant for all of these. So we're assuming that this numerator remains constant. Now pick which of these lists would give you the smallest SEB. So for starters, to have the smallest standard error, you want to have the largest sample size, because the larger the sample size, the smaller this fraction will become. So it's definitely not A. Next, to have the smallest standard error, you want your Sx to be as large as possible, because the larger the Sx, the smaller this fraction will become. So if you look at the list, Sx is just how the variability of your x variable. So you want the one that has the most variability here from letters B, C, D, and E. And that's going to look like letter E. That one has the most variability because you have just 3s and 27. So if you find the mean, it'll be, I don't know, 15 something. And then that has the most variability from the middle, from the mean, compared to the other ones where you have some numbers that are closer to the mean, like 15 and 21, or 15, 9, and 21. So E is the one that has the most variability for your variable x. Number 2, E. Why don't you try example 3 by yourself? Try it. Example 3. Okay. Oh, I don't want to give you the answer. Example 3. Try it. The standard error of the slope of a regression line increases when? Is it A, when the variability of the residuals decrease? Nope, because that's on the numerator. Is it B, when the variability of the residuals increases? Probably, yeah, that sounds right. C, the variability of the explanatory variable increases. Well, that's not going to be a no, because if Sx increases, the fraction gets smaller. Sample size increases, the fraction will get smaller. And then the y-intercept has nothing to do with it. So B. Okay. So again, make sure you know the formula and like how it relates to the standard error of the slope. Final thing, and that was easier. The final thing is just you need to know how to read a computer printout table. So that's example 4. Okay, here it is. Okay, example 4 says the data for the Y, which is the hours of sleep the previous day, and X, which is the hours of studying the previous day for 46 college students, was used in the following computer printout. Letter A says, what is the regression equation? So this is like back to first semester. The way you find your regression equation, you need a slope and you need a y-intercept. So here's where you find the slope and the y-intercept. On the first column, the one that says coefficient, that's going to give you your slope and your y-intercept. So the first one says coefficient of the constant. So this first row will always say constant, or it will flat out say intercept. That's the y-intercept because that's the constant of the equation. So 7.55 is your y-intercept. I called it A for y-intercept, it looks. And now the coefficient of like the second row here will give you like your x variable. So right now I put study because that was the number of hours you studied. Or sometimes it'll be like weight if that was your x variable. So this is always your x variable. So the coefficient of your x variable is what's called a slope. So in conclusion, the first column will give you the y-intercept on the top and then the slope on the bottom. So your equation would be y equals 7.555 minus 0.26917x. And we're supposed to write y and x in context of the problem. So x was the hour studying and y was the hour slept. And now the last thing you'll need to know is where to find the SEB, the standard error of the slope, because you'll need that. So the second column on your table, the one that says SE coefficient, those are the standard errors. The first one is the standard error of the intercept, but we don't do a test on that. So you will be looking at the one that's at the second row, the standard error of the slope. So again, I just labeled it on your table, I guess. Identify the 0.06616 as your standard error of the slope. In other words, SEB. We will need that to find our test statistic, which is, I guess, what we're doing on letter B. Letter B. Is there evidence of a relationship between the hours of sleep and the hours studying? Assume all the conditions have been met. Step 1, define your parameter. I just defined it. Beta equals true slope between hours sleeping and hours studying. Write your hypothesis. Is there evidence of a relationship? So it didn't specify positive or negative, so I guess we're going to go with a not equal to 0 for my alternative. And finally, like I said, you'll need the table data to answer this question. Find the test statistic and the p-value. The p-value is actually given to you already, 0.000. It's right there. But to find the test statistic, which I left blank on purpose, that's where you'll need that formula that I told you about the test statistic. So I'll show you one more time. The formula for the test statistic is equal to slope of your sample minus beta, which is always 0 based on your hypothesis, divided by the standard error of the slope. So based on our table here, we found the slope to be the negative 0.26917 minus 0, because that's always your null hypothesis, divided by the other standard error of the slope, so the other column, 0.06616. So now you know that the test statistic is negative 4.068. To find the p-value, like I told you, it already gives it to you right there on the table, but I think on the test I took it off as well, so you need to find the p-value for your test. So the way you would find the p-value is with a t-CDF, and this is an alternative hypothesis that had a not equal to symbol. So the way you'll find that is you're going to have to multiply your p-value by 2, like 2 times. So let me make sure. Let me fix it here real quick. That should be 2 CDF. So 2 times t CDF of negative infinity to negative 0.4068. I'm using 44 degrees of freedom because that's 46 minus 44. And then that's what I got. Let me make sure I did it right. Let's see. Did I multiply by 2? Yeah, that looks right. So almost 0. Your p-value is almost 0, which is what the table shows. And then you can finish the last part on your own. It says, make your decision and conclusion. Based on that small p-value, I reject the null hypothesis. There is evidence of some type of linear relationship. And so make your decision, conclusion. And then the last example 5, I'm not going to do it right now. You can just do it for practice. But that one is just asking you, are the conditions for inference met? So go through that process and see if the conditions are met or not. And then check your answers with the key. I think just by cheating, I look at the key right away. It looks like the conditions won't be met because your residual, the box plot of your residuals looks like it's going to be totally skewed, but just do it on your own. So here's my decision and conclusion. I did reject the null hypothesis. There is evidence of a relationship. I'll stop for questions, and your job is to make sure you study chapter 26, and then when you're ready, take the quiz before tomorrow night.